In an era defined by digital innovation, microchips are the unseen engines powering everything from our smartphones to artificial intelligence. Yet, the story of how these microscopic wonders are truly made often remains in the shadows. We interact with their creations daily, but rarely consider the intricate, highly specialized manufacturing processes that bring them into existence. At the very foundation of this entire industry, there is one company whose technology is utterly indispensable, a name few outside of the semiconductor world recognize, but whose influence is absolute. This is the story of ASML. From the complex calculations of a quantum computer to the simple on switch of your light, microchips are the digital fabric of modern life. They are etched onto silicon wafers with unimaginable precision, housing billions of transistors in spaces smaller than a fingernail. Each transistor acts as a tiny switch, controlling the flow of electrons, and their arrangement dictates the chip's function. The relentless demand for faster, more powerful, and more energy-efficient devices has pushed the boundaries of manufacturing to atomic scales, where conventional methods simply fall short. Headquartered in Veldhoven, Netherlands, ASML is not a household name like Apple or Samsung, yet it is arguably more critical to their existence. This Dutch company holds a virtual monopoly on the world's most advanced chip-making equipment, extreme ultraviolet, or EUV, lithography machines. Without ASML's EUV technology, the most advanced microchips, those found in the latest iPhones, cutting-edge AI processors, and sophisticated military hardware, simply could not be made. This singular position places ASML at the epicenter of global technological advancement and geopolitical power struggles. To understand ASML's significance, we must first grasp the fundamental process of lithography. In essence, lithography is the art of printing. But instead of ink on paper, it's light on silicon. Imagine taking a photograph. You expose a film to light, and that light changes the film. Similarly, in chip manufacturing, a pattern from a mask, often called a reticle, is projected onto a silicon wafer coated with a light-sensitive material called photoresist. This light transfer creates the intricate circuitry that defines a microchip's functionality. For decades, the semiconductor industry has been driven by Moore's law, the observation that the number of transistors on a microchip doubles approximately every 2 years. To achieve this, chipmakers must continually shrink the size of the features they print. These features are measured in nanometers, billionths of a meter. For context, a human hair is about 100,000 nanometers thick. Printing features just a few nanometers wide requires light with an extremely short wavelength, as shorter wavelengths allow for finer details and greater precision. Before EUV, the industry standard was deep ultraviolet, or DUV, lithography. DUV machines utilize argon fluoride excimer lasers, emitting light at a wavelength of 193 nanometers. While incredibly precise, DUV light has reached its physical limits in terms of resolution. To print features smaller than the wavelength of the light itself, engineers had to employ complex optical tricks, like immersion lithography, where a layer of water is placed between the lens and the wafer. But even these innovations could only push the technology so far, creating a bottleneck for further miniaturization. The next frontier demanded a radically shorter wavelength of light. The solution emerged in the form of extreme ultraviolet, or EUV, light, with a wavelength of just 13.5 nanometers. This is a staggering 14 times shorter than DUV light. Such a dramatic reduction in wavelength promised to unlock the ability to print far smaller features, enabling the next generation of microchips, chips with higher transistor densities, improved performance, and lower power consumption. The potential was enormous, but the engineering challenges seemed insurmountable, pushing the boundaries of physics and material science. ASML's journey began in 1984, a joint venture between Dutch electronics giant Philips and chip equipment maker ASM International. At the time, they were a small player entering a competitive market dominated by established Japanese and American companies. Their early years were marked by struggle, even facing bankruptcy at one point. However, ASML's founders had a clear vision to push the boundaries of lithography. This unwavering focus on innovation, coupled with a willingness to take enormous technological risks, would ultimately define their trajectory and set them apart. By the late 1990s, ASML made a monumental decision to bet its entire future on EUV technology. It was an incredibly risky move. The technology was decades away from commercial viability, requiring unprecedented research and development. This wasn't just about incremental improvements, it was about inventing an entirely new form of light generation and manipulation. The cost would be astronomical, requiring collaboration and investment from the entire industry. Skeptics were abundant, but ASML persisted, believing this was the only path forward for advanced chip manufacturing. Developing EUV was too complex and costly for any single company. ASML fostered a unique collaborative model, bringing together some of the world's largest chipmakers and suppliers. Intel, Samsung, and TSMC, fierce competitors in the chip market, invested billions into ASML's EUV development. This unprecedented cooperation underscored the industry's collective recognition of EUV's necessity. Each partner contributed expertise and capital, creating a shared stake in ASML's success, a testament to the scale of the challenge and the ambition of the endeavor. Generating EUV light is perhaps the greatest technical marvel of the entire system. Unlike DUV, which uses lasers generated from noble gases, EUV light at 13.5 nanometers doesn't occur naturally on Earth and is almost impossible to generate efficiently. It also interacts strongly with almost any material, meaning it cannot travel through conventional lenses or mirrors, nor even through air, making the entire process an engineering nightmare. Solving this required rethinking fundamental physics and material science, leading to truly mind-bending solutions. The ingenious solution ASML developed relies on a process called laser-produced plasma, or LPP. At its heart is a stream of microscopic molten tin droplets, each about 20 to 30 micrometers in diameter, smaller than a human hair. These droplets are precisely injected into a vacuum chamber at a rate of up to 50,000 droplets per second. The extraordinary challenge lies in hitting these fast-moving, tiny targets with extreme accuracy, a feat of engineering that defies easy comprehension, demanding unparalleled synchronization and control. As each tin droplet enters the vacuum, it is targeted by a powerful CO2 laser system. This isn't a single laser pulse, but a two-stage process. First, a pre-pulse hits the tin droplet, flattening and shaping it into a pancake to optimize the interaction. Then, an incredibly intense main pulse strikes the flattened tin droplet. This main pulse is equivalent to the power of a nuclear power plant, but focused onto a pinhead-sized area for mere femtoseconds. The precision and energy involved are simply breathtaking. When the main laser pulse hits the tin droplet, the tin instantly vaporizes and ionizes, transforming into a superheated plasma. This plasma emits radiation across a broad spectrum, but critically, it emits a burst of 13.5 nanometer EUV light. This conversion of laser energy into EUV light is highly inefficient, typically less than 1%. This means an immense amount of laser power is required just to generate enough usable EUV light for the lithography process. The challenges don't end there. This extreme environment creates unique problems for the machine's longevity. The EUV light emitted from the plasma spreads in all directions. To capture and focus this precious light, ASML employs a highly specialized, multi-layered collector mirror. This mirror is a marvel of engineering, coated with alternating layers of molybdenum and silicon, each just a few nanometers thick. It must withstand the intense heat and debris from the plasma while efficiently reflecting only the 13.5 nanometer EUV light. This collector mirror is the first critical optical component, directing the EUV light towards the rest of the system, a truly innovative piece of hardware. The intense laser pulses that generate plasma also create tin debris. This debris, if not managed, would quickly contaminate and degrade the collector mirror, drastically shortening its lifespan. ASML's solution involves a hydrogen gas flow around the collector mirror and a magnetic field that deflects tin ions. This system actively cleans the mirror, ensuring its reflectivity is maintained over time. Without effective debris mitigation, the entire EUV system would be impractical, making this crucial engineering feat as vital as the EUV generation itself. As mentioned, EUV light is absorbed by almost everything, including air. This means the entire optical path within the EUV machine must operate in an ultra-high vacuum, a vacuum so profound that it's akin to outer space. Any gas molecules present would absorb the precious EUV light, rendering the system useless. Maintaining such a pristine vacuum within a machine of this complexity and scale presents significant engineering hurdles, requiring advanced pumping systems and meticulously sealed components throughout the lithography tool. Unlike visible light, EUV light cannot be focused or manipulated using conventional refractive lenses, like those in a camera, because it would simply be absorbed. Instead, ASML's EUV systems rely entirely on reflective optics. These are highly polished mirrors that reflect the EUV light. The challenge here is immense. These mirrors must be manufactured to near perfect smoothness, with imperfections no larger than the size of an atom. If the surface of an ASML mirror were scaled to the size of Germany, the largest bump would be no more than a millimeter high. The creation of these impossibly precise mirrors is another testament to global collaboration. German optical specialist Carl Zeiss SMT, a long-term partner and part owner of ASML, is the sole supplier of these critical EUV mirrors. Their manufacturing process takes over a year for a single mirror system and involves layers of coatings applied with atomic precision. The development of these mirrors alone cost billions of euros and pushed the boundaries of what was thought physically possible, underscoring the interconnectedness of ASML's supply chain. Once the EUV light has been generated and precisely guided, it must then project the mask pattern onto the silicon wafer. This requires the wafer itself to be positioned with extraordinary accuracy. ASML's wafer stage systems are among the most precise machines ever built. They can move the wafer with nanometer-level precision, accelerating it faster than a fighter jet, while maintaining absolute stability during exposure. To minimize downtime, these systems employ a dual-stage approach, where one wafer is loaded and prepared while another is being exposed. The combination of all these mind-bending technologies results in ASML's flagship EUV machine, the TWINSCAN NXE series. These machines are massive, weighing over 180 tons, requiring 40 shipping containers to transport, and consuming megawatts of power. Despite their complexity, they must operate at incredibly high throughputs, processing over 100 wafers per hour. Each machine costs well over 150 million euros, with the latest models exceeding 200 million. This monumental cost reflects the decades of R&D and the unparalleled engineering contained within. ASML's monopoly on EUV lithography is not a result of market manipulation, but a consequence of unparalleled technological leadership and immense investment. For over 2 decades, ASML poured billions into EUV research, collaborating with the brightest minds globally, while other companies either abandoned the pursuit or lacked the resources to compete. The sheer complexity and astronomical costs of developing a viable EUV system created an insurmountable barrier to entry. No other company has successfully replicated ASML's capability, making them the sole provider of this crucial technology. ASML's innovation doesn't stop at current EUV technology. The company is already developing the next generation, known as High-NA EUV, with N8 standing for numerical aperture. High-NA machines will use even larger and more complex mirrors to collect more light and project even finer patterns onto wafers. This will enable chip features to shrink further, pushing past the current 3 nanometer nodes towards 2 nanometers and beyond. This continuous innovation ensures ASML maintains its lead, dictating the pace of miniaturization for the entire semiconductor industry. ASML's monopoly has thrust it into the very center of global geopolitics. Advanced microchips are now considered strategic assets, vital for national security, economic competitiveness, and technological supremacy. Nations recognize that controlling chip manufacturing capability translates directly into global power. The ability to produce cutting-edge microchips is essential for everything from advanced weaponry and artificial intelligence to 5G networks and critical infrastructure. This realization has ignited what is often referred to as the chip wars among leading global powers. The most visible manifestation of these chip wars is the intense rivalry between the United States and China. The US has implemented strict export controls aimed at preventing China from acquiring advanced chip manufacturing technology, specifically targeting ASML's EUV machines. Citing national security concerns, the US government has pressured the Dutch government to restrict ASML's sales to Chinese chip manufacturers. This move aims to slow China's technological advancement and maintain American supremacy in crucial areas like AI and supercomputing. The Dutch government finds itself in a precarious position, balancing national economic interests with geopolitical pressures. ASML is a jewel of Dutch industry, a major exporter, and a source of high-tech jobs. Restricting its sales to a major market like China carries significant economic implications. However, as a NATO ally, the Netherlands also faces immense pressure from the United States to align with its strategic goals. This places the Dutch government in a complex diplomatic tightrope walk, caught between economic prosperity and international security alliances. In response to these restrictions, China has redoubled its efforts to achieve self-sufficiency in semiconductor manufacturing. Billions of dollars are being poured into domestic research and development, aiming to create their own advanced lithography equipment. However, building an EUV ecosystem from scratch is an incredibly difficult and time-consuming endeavor. Experts suggest China is decades behind ASML's current capabilities, facing the same monumental technical hurdles ASML overcame with decades of focused effort and global collaboration. ASML's singular position also highlights the extreme vulnerability of the global technology supply chain. If anything were to disrupt ASML's operations, a natural disaster, a cyber attack, or geopolitical conflict, the production of advanced microchips worldwide could grind to a halt. This reliance on a single, highly specialized company for such a critical component is a source of concern for governments and corporations alike, prompting calls for greater diversification, though replicating ASML's technology remains an elusive goal. The economic impact of ASML's monopoly is profound. The company enables trillion-dollar industries, from consumer electronics to automotive and aerospace. Its advanced machines allow chipmakers to continue miniaturizing transistors, driving innovation and creating new markets. Without ASML's EUV technology, the pace of technological progress would slow dramatically, potentially stifling economic growth and delaying the next generation of digital advancements. The value ASML adds to the global economy far exceeds its own market capitalization. ASML's success is not merely about owning patents, it's about unparalleled, deeply embedded expertise. The hundreds of thousands of hours of collective engineering experience, the iterative refinements over decades, and the intimate knowledge of every microscopic detail of the EUV process are almost impossible to replicate. This tacit knowledge, held by thousands of engineers and scientists, represents a human capital advantage that is as valuable as any physical asset. It's a testament to sustained investment in talent and a culture of relentless problem-solving. Even after ASML's monumental machines are installed, their operation demands continuous, highly specialized support. ASML deploys thousands of engineers globally to provide maintenance, troubleshooting, and upgrades. These machines are so complex that they require constant monitoring and expert intervention to maintain peak performance and avoid costly downtime. This global support network is another layer of ASML's integrated control, ensuring that their systems, once purchased, remain reliant on their ongoing specialized services and parts. Looking to the future, ASML's role is set to become even more entrenched. As the demand for AI, IoT, and quantum computing grows, so too does the need for ever smaller, more powerful, and more energy-efficient chips. High-NA EUV and subsequent iterations promise to keep shrinking transistor sizes, but the physical limits of silicon are approaching. ASML's innovation will be key to pushing these boundaries for as long as possible, potentially exploring new materials or chip architectures in conjunction with their lithography advancements. While silicon remains the dominant substrate, the industry is constantly researching alternative materials and novel chip designs. However, even if new materials or 3D stacking architectures emerge, the fundamental requirement for ultra-precise patterning will likely remain. ASML's expertise in manipulating light at extreme wavelengths, combined with its unparalleled precision engineering, positions it uniquely to adapt to future shifts in chip technology. Their core competence is not just in silicon lithography, but in the most advanced forms of nanomanufacturing. In summary, ASML represents the ultimate bottleneck for advanced microchip production. Every company that wants to make the most powerful, cutting-edge processors must, by necessity, go through ASML. This Dutch firm doesn't just sell machines, it sells the future of technological progress. Its unparalleled mastery of the mind-bending physics of EUV light generation and its engineering prowess has created a single point of control over the digital infrastructure of the modern world. This makes ASML an entity of immense strategic importance. Consequently, ASML is not merely a company, it is a critical geopolitical chess piece. Its technology is a tool of national power, influencing trade relations, military capabilities, and global economic hierarchies. The ongoing chip wars are, in many ways, a proxy battle fought over access to ASML's innovations. As long as advanced microchips remain vital to national interests, ASML will continue to be at the forefront of these intricate power dynamics, an unwitting but essential player in shaping the global order. From the intricate dance of molten tin droplets and high-powered lasers to the quiet hum of a multi-billion-dollar machine in a pristine cleanroom, ASML has mastered the art of creating light from chaos. It is the unseen architect of our digital world, the company whose name few know, but whose creations touch every aspect of modern life. Its story is a profound illustration of human ingenuity, relentless pursuit of scientific advancement, and the unpredictable forces of geopolitics converging on a microscopic scale, determining the future of technology and global power.